So now we have Dr. Arndt von Twickel from BSI, the Federal Office for Information Security, coming up. And Arndt, you are, since 2023, heading the Division of Cybersecurity for Intelligent Transport Systems and Industry 4.0 in Bonn. And in the department DI, Cybersecurity and Digitalization and Electronic Identities, you were and continue to be engaged in areas of biometrics, automotive, and leading working groups and cyber strategizing, so to speak. And before joining the BSI, you worked at various research institutions in the fields of neurobiology, neuroinformatics, also robotics, and also held various teaching positions. And I hear you're very busy man beyond your work as well. So thanks for being with us, and over to you.
Yeah, thank you very much, Patrick, for the kind introduction. And yeah, welcome again. I will today talk about auditing AI cybersecurity, combining vertical and horizontal approaches. Just to make the context clear, I will give you an example from a typical day in a modern car. So we have challenges and opportunities. So maybe we start the journey by opening and starting the car via an app or via biometrics, which uses AI. We can do route planning and optimize configuration, again using AI technology. Then we have different comfort functions during the ride, like infotainment, language assistant for scheduling appointments, predictive maintenance functions, and so on. We have, of course, the autonomous driving functions coming more and more on the roads, including perception functions, decision-making, car interior surveillance, and so on and so forth. And of course, we have, as another component, e-charging. So we need to have automatic navigation to the charging point, AI-optimized charging functions, and so on. And the point is we have a lot of interfaces, a lot of functionality, and this, of course, increases attack surface for attackers, so malicious people out there that want to do bad things. And the point is they can also use AI. So AI not only helps us with the functionality, but AI can, of course, be used to increase the capability of the attackers. So we have to secure these systems. And securing the systems, we can also make use of AI technology to secure the system. So it's like the cat and mouse game always, who is a little bit more in advance. In reality, it's really the attacker are always a bit ahead because the system is so complex. It's really tough to secure the system. You can only reach a certain level of trustworthiness and cybersecurity here. So to sum up, the use of AI leads to new protective functions, but at the same time also to qualitatively new cyber attacks and also quantitatively. So the mitigation of AI cybersecurity risk necessitates the consideration of multiple criteria. So as I said, we need to ensure cybersecurity despite of adversarial AI. We need to have cybersecurity for AI systems, so we need to make AI systems secure despite their new properties. And we need, we can use AI for cybersecurity. And on the one hand, we need to consider use case specific or so-called vertical criteria from the different domains. So we heard this in the TÜV AI lab talk before. So for example, we might consider medical products, financial services, automotive industry, and so on and so forth. And on the other hand, we need to look at use case overarching criteria, so-called horizontal criteria. We also heard this in the TÜV AI lab talk. So for example, life cycle from development to decommissioning and supply chain criteria, technological criteria like machine learning models, LLMs, and so on, and the different aspects like performance, robustness, transparency. This has all been nicely summed up in the talk before. So I won't go into this more. So I will dive into different examples. So one example for an horizontal approach is for developing AI security requirements and audit processes is a so-called software bill of materials for AI, so a parts list for AI systems. So the software parts list for classical software and for AI looks as follows. So the status quo is a technical guideline for classical software, but this has been found not to be sufficient for AI because the dynamics of AI is not taken into account. So the software bills of materials is something that is automatically creatable, analyzable file that contains supply chain relations and details of the components used in a software product. So as you can see, I don't know if the laser does not seem to work. So basically, it's example is shown here. So a common format for this exists and a BSI guideline for the technical operationalization of this SBOM. So the SBOM for AI, what is different? On the one hand, AI is software, so we need to have the SBOM, but the AI contains, besides static, also dynamic elements that have to be taken into account. And the goal is to have transparency in this AI supply chain and sufficient transparency really to really deal with the new AI issues. So the dependencies along the AI supply chain, where you go from supplier to manufacturer and to users, always with AI as a delivery item, are that at the supplier level you have data sets, for example, training data, you have AI models, for example, the original model and training methods, and you have third-party libraries. On the manufacturer level, you have data curation, for example, with respect to bias. You have a fine-tuning of the model with respect to parameters and validation and test methods. And you have, of course, interfaces that might be added or modified. And on the user level, you have end users and developers. So the transparency of the supply chain is a precondition for AI security or prerequisite. So the BSA lays the foundation here. At the SBOM for AI level, a structured recording of the components of the AI system. There's currently a technical guideline being developed in the G7 context led by the BSI. So I will point you to the documents later on. So the horizontal approach, there's another example here. It's a quality criteria for AI training data throughout the AI lifecycle. There's a challenge to operationalize the available criteria for AI training data. So we have a lot of different guidelines, norms, and standards. So shown here on the left side, most importantly, maybe the AI Act, but then also different ISO norms, different other guidelines, norms, and standards. And we counted at the BSI that there are at least 73 of them. And the challenge now is to transform these criteria. Some of them are listed here, like accuracy, reliability, transparency, stability, structural integrity, and so on and so forth, to metrics and actions. And these criteria are often very abstract and have multiple redundancies. So the idea is that you make this more concrete. You go from the abstract criteria to building blocks, to measures, and then to metrics and methods. And so we published different documents on this, on the definitions and foundations, the quality criteria and building blocks, and the metrics, and also published the source code. Here's the link. And also we went a step further and made this available in a relational database on GitHub. So there are two repositories if you're interested. So the first repository gives this as relational context as SQLite, Markdown, and JSON, and allows a quick generations of subsets of metrics for single quality criteria. And the repository B gives simple example implementations of every metric. And the source code is in Python here. And then as a vertical approach to developing AI security requirements, I will take the automotive example again. I think we presented this in more detail last year. So we have at first a very complex regulatory landscape in the automotive domain. And here a selection of relevant laws and regulations for cybersecurity and AI is shown. So to explain, on the left side, you have consumers, infrastructure, and products that need protection. And so all these laws and regulations intend to protect these. And on the other side, you have authorities, service providers, operators, data users, and manufacturers that need, where the laws and regulations put obligations into power. So, and the challenge is that for this AI Act, Data Act, GDPR, Cyber Resilience Act, NIS2 Directive, UNC ECE Regulation and R155, you need to cope with these challenges of, for example, overregulation, distributed responsibilities, different reporting processes and timelines, and for especially with a topic of operationalizations. We heard this in the talks before. And this specifically is true for the AI Act. So we will soon publish, beginning of next year, so the draft is available if you're interested, a technical guideline on AI security in automotive. So this is from our side a contribution to this operationalization. And this describes a process to translate existing sector-specific security and safety standards in generic and use case-specific AI requirements. So how does this process look like? So we start from standardization and best practices. We add AI or model-specific properties and derive at generic requirements. Using the specific use case or the use case-specific information, for example, from automated driving, we can then derive specific, or we can specify these generic requirements to specific requirements, evaluate these in exemplary audit processes from simulation testing to practical testing, using different test criteria, using then again data and scenarios, methods, tools, and AI models. And of course, we have to consider the AI system as an integrated part of a whole bigger system. And we focus on technical depth and practicality. We developed 50 generic requirements and evaluated them by means of exemplary audits. So here's one example shown from generic requirements to the practical evaluation. Here the results from the use case pedestrian detections are shown. For example, there's a generic requirement: the AI model shall be resistant against possible robustness threats. This has been specified to the requirement: the AI model shall be resistant against malicious input perturbations. And the test criteria have been derived. One of them, the AI model's performance should be above a threshold of 90% accuracy for correctly detected road users on a defined test set containing adversarial examples. So we performed different tests on the test track in simulation and so on. So you see here different adversarial examples, like here with this dog face. So we did this in simulation and on the test track. And the final verdict here is based on the physical test scenarios. And here the test was partly passed. So with some of the examples, the systems, so we tested open source, self-trained systems and commercial systems. For a lot of examples, the systems were robust, but for others, they were not robust. So the systems don't work perfectly here yet. So what are the next steps? We think it's now important, as Patrick pointed out, we need to come into action now. So the things have to start working now. It has to go beyond concepts and academia. So we need to have a fast, iterative improvement with short cycles of AI security requirements and audit processes by further integrating horizontal and vertical approaches, adding results of further sectors and use cases. So for example, at the BSI, we already looked at the financial sector, the medical sector, biometrics, and the agricultural sector. But others are important as well, and refine the model every time of how to audit and test the system. Then we want to contribute, or we are already doing this, the results to national and international regulatory and standardizations efforts. For example, in automotive, to the UNECE WP29 informal working group on AI. Then the plan is, because as Patrick also pointed out, more and more products are coming onto the market that need to be audited really. So we need to now employ and evaluate the developed requirements and audit processes in real approval processes and really take the lessons learned and improve our processes. And of course, then we need to extend the view from the AI systems to complex systems, because the AI is only part of the whole bigger systems. So I think in the end, we have to talk about complex systems, at least in the case of robots and automotive systems. And at the BSI, as Patrick also pointed out, we have a lot of publications on different AI cybersecurity topics. Just to give you a few examples, We have now a new guideline for penetration testing of large language models. We have a paper on evasion attacks on large language models. We have a paper on reinforcement learning security in a nutshell. We have this SBOM paper in the G7 context I talked about. We have these white papers from our previous workshops here, a paper on AI coding assistance, and so on and so forth. So if you're interested, just visit our website, and if you have questions, just contact us at any time. And with that, I would like to thank you for your attention, and yeah, I'm open to any questions now or during the break.
Questions?
Hello, thank you very much for your presentation here. I'm Alexander from TU Delft, from Netherlands. I have a question about assessing autonomous driving pipelines. There are new pipelines available in the not on the market, but heavily researched, end-to-end path planners. And how would you approach evaluating those planners? Do you plan to evaluate them in the nearest future, or you stick to more modular approach? Thank you.
Yeah, thank you for this question. I think you hit a very important topic. It's a trend from more modular systems to more end-to-end systems, which makes, of course, the task of auditing these systems much more complicated, because we already have the problem with AI systems. I mean, Wojciech just showed us a way of more looking into these systems, but it takes a lot of work. It's not just that simple. So really looking deep into these systems, understanding what they're doing is really a tough and hard task, and it's not readily available for all of these systems. So it's already tough for these modules. And if we go to these end-to-end systems, it's even more complicated. So what we need to use is empirical testing. And there, of course, as you know, the parameter space and input space of these systems is huge, so that takes a huge amount of resources. So what is really important is to find out what are the critical inputs that need to be tested. And I think this is very important, but I don't really know how far we can get with this. So we need to start and see then in practice testing. We talked about sandbox systems. Now we have first autonomous cars on the street that are being tested. And we need to go step by step, I think. So there's no one-size-fits-all solution at the moment, but a step-by-step approach, increasing these approaches from explaining these systems and also of identifying the most relevant inputs that need to be tested and introduce more automation in these testing, from simulation testing to the real track testing. So I think you need multiple approaches. It's not a simple task. Yeah, you're welcome.
Thank you, Arndt. Another round of applause.